I would like you to please welcome Daniel Kosevsky. Please tell me I got it right. Nice, I got it right. Stellar evolution and what it has to do with your iPhone, or in my case, Windows Phone. I'm probably the only one here who has one.
Yeah, so I'm Daniel Kosevsky. I'm at Stanford. I do astrophysics at Stanford, and I'm going to be talking about all of the elements that go into producing all the gadgetry that we are in love with. So in this room, let me see a show of hands for iPhone users, and then I'm going to ask Android users. iPhone users and Android users. Let's see the Google employees. Oh yes, there it is.
Windows Phone users.
Okay, Windows Phone. Okay, so yeah, we're going to be taking the perspective a little bit further out into space here, but these are two wonderful talks to be following up. Hold on. Yes, please. Let's see if I can. Okay, as we made, I'll tell a joke. An atom walks into a bar, Adam walks into a police station and says, "Officer, I've lost, someone stole one of my electrons." And the officer says, "Are you sure?" Right? And he says, "Yes, I'm positive." Okay, so here we go. Yeah. Yes. So, if you think about, you guys have, there's a tech-heavy crowd. So we have our iPhones, and we're sitting at home, texting our friends, and at the same time, we are, watching what, of course, we're all nerds here, so we're watching Star Trek on our iPad, and we probably have an Apple TV, and we're streaming that over to our, big screen, and we're cranking out that sound on huge speakers. And when you think about it, the elemental composition of what that's needed to make this all operate is pretty staggering. I mean, this is, in the iPhone alone, you have, in the plastics, you have carbon, sulfur, oxygen, nitrogen. In the glass, you get silicon and oxygen, aluminum in the case, lithium, cadmium, some of the older batteries, semiconductor, silicon, germanium, very high Z number elements, copper, tin, silver, gold, much more. They go into this one device. And we have over 100 elements in the periodic table, and the fundamental question becomes, how did these elements come about? Where did these come from? And why, for example, is uranium much less common and much more rare than, say, iron or oxygen or hydrogen? And what processes produce these elements? And the one thing that we know for sure is that these elements didn't exist at the beginning of the universe. So we know that the conditions that happened in the early universe basically prevented any of these elements from existing. And to understand why, we recap real quick that elements are basically atoms that have ever more complex configurations of protons and neutrons. So hydrogen just has a proton orbited by an electron. A helium atom is simply 2 protons, 2 neutrons, 2 electrons. Lithium is ever more complex. We have really good observational evidence that in the early universe, that the conditions in the early universe were so much more dense and very high temperature. Basically, the universe was really small, so everything was pushed into a small space. And so this spot, this T equals 0 back here, represents what we call the Big Bang. And soon after the Big Bang, the universe was so hot that neutrons and protons couldn't exist. They were smashed in together, and what you get are basically the quarks, the fundamental particles that we know that are inside protons and neutrons. They're the only things that exist. So we have this quark and gluon soup or plasma at this early time. This is 10 to the -6 seconds or so. And after the universe expands a little bit, cools down, these quarks can then come together and form the hadronic matter, protons and neutrons. And soon after that, around 300,000 years later, the electrons bind to those things and we get the first atoms popping up. So we have hydrogen atoms and helium atoms. And at this point, the universe is made of pretty much 75% hydrogen and 25% helium, and there's almost nothing left, or nothing else. I mean, there's very small traces amounts of lithium there, but the universe is completely made of these very two light atoms, these two gases, here on Earth. And it takes another couple 100 million years, 300 to 400 million years, that the first stars start to appear on the scene. And it's these stars that basically produce the wide variety, the richness that we see in the universe. And then those stars, of course, go on to form galaxies, and they form all the structure that we see in the night sky when we look up. And that's 13.75 billion years later. So to understand why stars are so important in this process of enriching the universe, we have to look at, review the fundamental forces really quickly. So we have gravity. There's 4 fundamental forces that we know of. There's gravity, which attracts all matter. Basically, it's what makes the moon orbit the sun, or so the moon orbit the Earth, and the Earth orbit the sun. We have electromagnetism, which is basically the force that attracts opposite charges and repels like charges. We have the weak force, which we're not going to talk too much about, mediates radioactive decay. And then we have the strong force. And the strong force binds nuclei together. So if you put 2 protons, or a proton and neutron close enough, the strong force will kick in and bind those 2 together. Now, the electromagnetic force and the strong force are working in opposite ways, because if you push 2 protons close to each other, the electromagnetic force will actually push them apart. Just like when you take two magnets and you push them together, you're going to feel a force pushing them apart. So what happens is that if you have enough energy and you push those 2 protons in close enough, the strong force will kick in. It'll overwhelm the electromagnetic force, hence the name strong force, and it'll bind those two protons or those 2 neutrons together. And so this is why, for example, it's really hard to create elements. This is why, for example, people's efforts to transmute other elements into gold fail back in the Middle Ages, because you need really high energies in order to overcome this electromagnetic force. And it's only been through the advent of modern particle accelerators that we can actually do this on Earth. But a place where this happens all the time and very easily is at the center of stars. And so the star is, a star like our sun, has a huge amount of matter pushing down on its core. And so that you have this gravitational force pushing down and creating a high pressure and high temperature region in the center of the star. And this causes that region to heat up. And when you look inside there, what you see is basically protons moving so fast and with such a high energy and high density that they can collide and form helium. So those 4 protons basically are hydrogen atoms without their electrons. Everything in the core is ionized, so their electrons are not part of that picture. And so those hydrogen atoms come together, form a helium atom, and then release an enormous amount of energy in doing that. And that's why fusion reactions are thought to be basically it would be the key to solving the energy crisis on Earth. If we could do this in a lab, you would get an enormous amount of energy out. And the reason this is because these 4 protons, if you add their mass together, their mass is actually, they weigh more, the sum of the 4 protons weigh more than 1 helium atom. And the difference in mass comes out as energy. So it just equals mc squared, so you have a difference in mass between these products, and the difference comes out as this energy. And this is commonly referred to as thermonuclear fusion. Basically fusion that's brought about through high pressure and high temperatures. And so the energy that these reactions produce in the core of the star basically support the star. They're pushing out against the forces of gravity and balance out that force, and the star is in hydrostatic equilibrium. And this is basically the condition that our sun is in. The sun is burning, fusing hydrogen in the core, and that's counteracting that force of gravity, and the star is stable. So our sun's been doing this for 5 billion years. It'll probably do this for another 4 to 5 billion years. But then the process is will not last forever. So the sun, for example, and very massive stars, even more so, are giving off enormous amounts of energy. So, for example, somewhere of 10 to the 2400 watt light bulbs every second are being emitted by the sun. And in order to generate that much energy, the sun has to go through 5 million tons of hydrogen per second. So it's basically consuming all the hydrogen that it has in the core of the star. And so, sure enough, over time, that hydrogen will get depleted, and the reactants of this fusion process are going to cease. And when this happens, the energy that's coming out of the fusion is going to basically stop, and gravity is going to win, and its gravity is going to start contracting the core. And when it does this, it heats up the core even more, and it gets hotter. The core basically gets to a higher temperature, higher density, and it basically gets to the point where it can start to fuse helium. And so each element on that periodic table requires more and more energy to fuse those two elements to create the heavier element. So for example, once the core starts to contract, temperature heats up, the helium atoms get sufficient energy where they can combine, collide, and form beryllium. And then that beryllium atom collides with another helium atom, and you get carbon-12. And so by this process, and this of course releases more energy, that energy counteracts the force of gravity, the star gets balanced out, and then everything is all good for a little while. Eventually, of course, it's going to run out of helium, and then the core is going to contract again, and it's going to start burning carbon, and then eventually it'll run out of carbon and keep going up the chain of elements. And it'll keep doing this for very massive stars that are much more massive than our sun, for example. It'll keep doing this for successively higher elements. It'll start burning carbon when it runs out of helium, it'll start burning neon when it runs out of carbon, oxygen, then silicon, and the last stage is that it starts burning silicon into iron. And the different phases for a very massive star, one that's much more massive than our sun, the helium burning phase will be about 7 million years, and then the hydrogen burning phase will be 7 million years, helium 500,000 years, carbon 600 years, neon for 1 year, oxygen 6 months, silicon 1 day, and then when it starts burning iron, that lasts for 1 second. And there's a very interesting reason why the iron station there doesn't last very long. These previous reactions that I've talked about, they are all exothermic. So when you combine these atoms together, you get a net energy gain. And so that net energy gain supports the star under the force of gravity. And so this process of fusing two iron atoms together, on the other hand, to form a nickel atom is actually endothermic. So it sucks up energy. And so once the star starts fusing iron into nickel, the game is over and the star is all hope is lost for the star. Basically, this reaction saps all the energy out of the core, and the core immediately contracts under the force of gravity, collapses, and for a very massive star, forms into a black hole. There's two stages that could either form into a neutron star or a black hole, depending on the mass and depending on the force of gravity. But if the core is large enough, it will contract and form a black hole. And then that will set up a shock wave that will go out and immediately destroy the star within seconds. And then what's left behind is some black hole with material circling around it, and that's what we see. We can see X-ray and gamma ray emission from these accretion disks that form the black hole, and that's how we know that the black holes are these leftover remnants. Now, the supernova itself, what we see observationally is the supernova itself ends up being an enormous explosion. So you have here, for example, the supernova going off, and it's brighter than the entire sum total of 1 billion stars in this galaxy. So the explosion itself is incredibly energetic, and we see for some of these very massive stars, the ones that I study, which we refer to as gamma ray bursts, that give off a lot of energy in the X-ray and the gamma ray, we actually see that they give off as much energy as the total rest mass energy of the sun, for example. So if you were to take all the energy of all of the mass of our sun and convert it directly to energy in the most efficient way possible, just taking E equals mc squared, we see that amount of energy coming out of these objects just in light. And so, to say nothing about the kinetic energy, right, of everything getting blown out into space. That explosion is incredibly energetic, and I'll get back to that in a second. But this fusion process at the core of these stars can explain everything up to about iron and nickel, between these heavy elements right around iron. Nickel being produced very briefly at the center of these stars. So the question becomes, how do you produce all of these other elements, right? All the other heavy what astronomers refer to as just metals, all of these very high Z atoms. And so to understand that, we go back to this explosion. The explosion itself is incredibly energetic. And so when the shock wave bounces off the core, if it's a neutron star or somehow gets ejected by this black hole, that shock wave mixes up all of these elements. So it takes the iron and the silicon and the oxygen and pushes it out to the outer edges of the star, and then suddenly iron atoms are encountering hydrogen atoms and other byproducts of the fusion that's going up in the higher regions of the star. And so when you look at what's happening with the shock wave, you have basically these very high energy, very high Z elements. These basically elements with a lot of protons and neutrons in them, like iron and silicon and nickel, and they're being carried up by the shock wave, and they encounter free neutrons and free protons that are out in the outer edges of the star. And this neutron flux, basically, the amount of neutrons that it sees is incredible. It's just basically we're plowing into the outer edges of the star. So every time it does that, it captures one of these neutrons, and it makes it into a heavier isotope of that atom. So for example, iron 56 becomes iron 57. It goes on and hits another neutron that becomes iron 58, so on and so forth. This is called neutron capture, and it's basically the way that we explain how anything higher than iron exists. Of course, just adding neutrons to an atom doesn't produce a new element. It just basically produces an isotope. You have to add more protons to an atom in order for it to be considered a new element because of the way we define elements. So when you run into more neutrons, what ends up happening is you get ever and ever higher neutron content in these elements and in these atoms. And just like and when you add neutrons to a nuclei, it becomes more and more unstable. So just like uranium-238 is a really good fission source because it's very unstable because it's overloaded with neutrons and it's always trying to get rid of those neutrons. And this is why it's used in nuclear bombs, for example, because those neutrons go out, hit other uranium atoms, and split them apart, and you get this chain reaction. But what ends up happening with, like, say, iron 459 is you have one of these neutrons decays into a proton and an electron and shoots off the electron, and then you get cobalt 59. And then cobalt runs into another neutron, makes radioactive cobalt 60 that decays into nickel 60, and so on and so forth. And these other atoms hit into more neutrons and become heavier and heavier. And so through that process, you can pretty much explain all of the rest of the elements that we see. So this it's called neutron capture. R process and S process are rapid neutron capture and slow neutron capture. So from there, these stars, of course, then explode and shoot out all of their elements out into space. And what you end up getting are things like this. This is actually a planetary nebula. It's a star that was less massive than the diagram that I showed you, but it basically ejected all of its outer layers of the star out into space. Supernova remnants do the same thing. When a supernova happens, it sets up this shock wave, and the shock wave travels through space, and then you can kind of see the shock wave up in the right there, traveling out. If I have my pointer. Yeah, you can see a shock wave there traveling out into space. That shock wave will run into other gas, other material in the galaxy, and compress that gas and form new stars. So basically, these shock waves from previous supernovas will go out and collapse gas. Eventually, this gas here that's surrounding this nebula will eventually cool, coalesce, and form clouds, molecular clouds in space. And this is the famous Eagle Head Nebula, which you guys have probably all seen. This is basically gas that has been enriched by the explosion of previous stars that is now coalesced and cooled. You have, in this case, very bright, very massive stars up here that are shooting down ultraviolet light, and that's causing this gas to evaporate. That's what we're seeing with these kind of really cool lines coming off of it. But if you look at these little knots and spots in here, like that guy, if you zoom in there with Hubble, you can actually see that they are little knots of gas. And so little guys like this that you see they're basically absorbing all the light, and they're very bright in the infrared, but not bright in the visible light in this, which is the wavelength that this picture was taken in. These guys are protostars, and these stars are now forming and collapsing out of the gas that was enriched by previous generations of stars. And once these guys cool and coalesce, you end up getting one of these kind of disks, debris disks of, basically you get to some point where it gets massive enough at the center where the star collapses and hydrogen fusion can occur in the center of its core, and that's when the star is born. All this other stuff that's outside, what ends up happening is once that hydrogen ignites, the radiation from this star starts to eat out this disk, just like we were seeing that light from those bright stars eating away and evaporating the Eagle Head Nebula. The same thing happens here, and all of this, it basically clears out a zone in the center of the star that prevents this stuff from falling in, and then all of this gas then coalesces to form the planets that we know and love. And the planets, what's really interesting here is that the amount of, so we have all of the rocky elements, the very heavy elements in the inner planets, the inner four, Mercury, Venus, Earth, and Mars, and then we have the gas planets outside. So the gas planets are basically made up of all of the outer layers, basically the gas that was left over from the outer layers of these stars, so hydrogen, helium, things like that, and all of the iron and nickel and uranium, all the heavy elements are coalesced in the inner disk, and that's just because of gravitational differentiation. You get heavier elements being pulled into the sun, and the other guys being pushed out. And you have also these lighter elements couldn't exist in the inner part of this debris field because they get evaporated and pushed out by the radiation from the sun. But what's really neat, though, is the amount of heavy elements that we have in, like, say, in the Earth. For example, the Earth is almost completely made of iron. And we see lots of water and oxygen, but it's just right on the crust. I mean, inside the planet, a huge fraction of the planet is made of iron. So the amount of iron that we see, and that's the case for almost all of the interior planets. So the amount of iron that we see, remember the iron was fusing there for 1 second. In 1 day, silicon was fusing into iron for 1 day, and so then iron fused into nickel for 1 second. The amount of iron that we see on the planet means that there must have been hundreds of thousands of generations of stars that existed before us. So the Earth is 5 billion years old, 4.5 billion years old. The Sun is about 5 billion years old, we think. The universe is 13 billion years old. So there are successive generations of solar systems that existed here before us, before all of this came together, in order to explain where all the metals came from. And so, in order to have complex life that we as we do, for example, iron being the method in which oxygen is transported in our blood and things like that, all of the mechanisms, not only in our gadgets but in life itself, depended on these successive generations of stars to enrich the environment. And that produced, of course, all the rich diversity that we see here on Earth. And so all of the organic compounds, the carbon and hydrogen there, the water, the hydrogen and oxygen in the water, all of the minerals, uranium in the soil, the granite, and of course all of the beautiful things that we take for granted here.
And all the reef fish.
And yeah, exactly. And all of the wonders that we have here in this beautiful city were basically, all of this matter was once at the center of a star. It was all at the core of stars that lived millions and billions of years ago. So I'll end there and take your questions.
So when a star goes supernova, why is the accretion disk two-dimensional? Does that mean that Star Trek got it right?
Yeah, no, Star Trek got it right. They had science advisors, I'm guessing, that knew that accretion disks are flat.
Can you repeat the question?
Yeah, so he asked, when a star goes supernova, we see accretion disks around the remaining black hole or neutron star that's left over. The question is, why are those accretion disks flat? It's actually just conservation of angular momentum. So the star was spinning when it exploded. It's the same reason, for example, that we see these planetary disks are also flat. And if you look up at the night sky, for example, so the planets form out of this disk. The disk is rotating in some fashion, say counterclockwise. The sun ends up rotating. The star that forms ends up rotating in that fashion. If you look up in the night sky, for example, if you see there's like a Venus and Jupiter typically up in the night sky at certain times of year at the same time, you can see that they actually all form a line in the night sky. So if you look, especially when Venus is on the western sky and the sun just set and the moon is up and Jupiter's in the sky, for example, you can see that there's the sun set, then there's Venus, and then there's the moon, and then there's Jupiter, and they're all in one line. and that's because of this disk, the disk that everything coalesced from. And so if you look actually with a telescope and see the direction in which Jupiter and Venus are orbiting or spinning, and the direction in which they're orbiting the sun, and the direction in which the moons around Jupiter are orbiting Jupiter, they're all in the same direction. They all are in the same direction as the moon goes around the Earth, because the angular momentum basically was conserved in this whole process. It's very hard to lose angular momentum. It's only through collisions and things like that. So if anything ventured above this disk, it would basically collide and basically kind of be ejected out or fall back into the disk. So that's the short answer to that.
You made a combinatorial argument how
Yeah.
does that imply that there is no other mass? Is there like a sweet spot?
Well, the sweet spot actually is iron. Yeah. So the question is, because of this kind of hierarchical method of like building up elements, are the elemental, kind of the fractions and the abundances, are they logarithmic? And I don't know exactly. I mean, it makes a lot of sense, but I think it actually depends on, for example, the binding energy of the nuclei. For example, iron has, iron has the highest binding energy of atomic nuclei. And so, if you have helium, if you push add neutrons and protons onto helium, it contracts and gets tighter, and that's a lower energy state than for example, the hydrogen, helium, and things like that. So everything tends to go toward iron. So you fuse things together. If things get fused together, form iron. All the elements above iron are breaking down and radioactively decaying to iron. And it's actually, when people talk about the heat death of the universe, not only are all the stars going to die and all the energy is going to be lost in fusion, but then all of the nuclei will decay, and basically the universe is going to be full of iron atoms. And so that's like the lowest energy state is iron. So I know for sure that it's not just a logarithmic scale from hydrogen to uranium, that there is this valley of stability at iron. So it's a little more complex. Yeah, back in the back.
So you said that the heavier elements were accumulating from multiple successive star formations, but 13 billion divided by 5 billion comes out to about 2.5. So.
Yeah, so stars like our sun can last for 10 billion years or so. But stars that are much more massive than our sun, so the stars that are thought to have existed at the really early beginning of the universe, they can last anywhere from 5 to 10 million years. So they live twice as bright and half as long, right? So they are consuming their fuel in a much faster pace than our sun, and they can burn out very quickly. And we can see those stars. Those are the stars that were illuminating the Eagle Head Nebula, for example. Sorry, the question was that stars, why do stars, if the sun has been around for 5 billion years and the universe is 13 billion years old, then how many generations could you possibly have had? And the answer is that stars have a very diverse lifespan, and it depends on their mass. So stars that existed in the early universe were more massive because they had less metals, and metals tend to have all kinds of excitation lines, and those lines cool the star very efficiently, and so it prevents them from getting very massive. And so stars like our sun are very late generation stars, and they will last for a very long time as a result. But we still see, even in our galaxy, stars that have lifetimes of 10 million years or so.
Daniel, you can take one more.
Okay.
Do you believe there's anything along the lines of like sea of tranquility outside, like far outside the elemental table?
Yeah, there are.
Repeat the question.
Yeah, so the question is, are there islands of stability in the periodic table, right? And if anyone saw Iron Man 2, he finds one of these elements in the movie. He creates a new element that's stable way out there. So the idea is that if you add more and more neutrons and protons to a nuclei, these elements up here tend to be very unstable and very short-lived. But there are a few of them, I Yeah, so there's a few of them. I'm not 100% sure which one up here that's very stable. So the idea is that there may be configurations of neutrons and protons that go beyond here, which are artificial that we don't see in nature, but you could slam together in a particle accelerator, for example, and find an element that's stable because its configuration of neutrons and protons it just happens to be in some way that it won't decay. We haven't found anything like that in nature. If it existed, it would be very, very rare. But there are people that are working on trying to find those kind of things.